All right. So I will show Trotter Suzuki in a moment, but first I want to discuss a couple of things about the matrix norms that we were discussing. So if I have a matrix, I can take the operator norm of this, and this is the largest singular value of the matrix A. And for this, there's a couple of tricks. First of all, you should be aware of the singular value decomposition. If you search on Wikipedia SVD, then you will find nice articles. So you can also ask me. I will just define this in a second. So SVD is the choice of two appropriate unitary operators V and U. So V and U are in unitary operators of dimension D, and the dimension of the operator A will be also D. Yeah, and lambda is diagonal. Okay, so this is called the singular value decomposition, and probably we have one dagger somewhere. And this is different from diagonalization. Because for diagonalization, we would be searching for something like U lambda U dagger. Okay. So for diagonalization, we can get for operators which are normal. So A is normal if basically there's some commutation relation. If we have this property, then diagonalization is possible. Okay, so I'm not spending time on defining SVD. I'm not spending time on defining what normal is. That's all quite easy checks on Wikipedia. What I want to say is that normally we would have that A is equal a dagger, and then A in particular is a normal operator. Okay, so that's why usually we don't talk about this, and we talk about this because this is a Hamiltonian in quantum mechanics. Okay, or an observable would be also Hermitian. Okay, that's why this. This is for Wikipedia. Singular value notation also would be Wikipedia. This is also Wikipedia, and this. I want to show you some properties of the singular values. So I will rewrite the same thing again. So if I have an operator, the operator norm of that operator A is its largest singular value. And now how to compute singular value is actually very interesting, because singular values also exist for matrices where you cannot diagonalize, and maybe for rectangular matrices and so on. So so what we have is that you consider A dagger A and then diagonalize this. So, for example, homework 1 today could be show for all A in C n by M, A dagger A is normal. Okay, so that's actually a very interesting construction to be forming this. One example, besides this kind of small homework, this is just if you want to understand more this normal condition and so on. Another question here would be, what is A dagger A and A dagger if n is not equals to m? Okay, And the point is that they will have differing spectrum, but they will differ only by zeros in the spectrum, and the non-trivial spectrum will be preserved. Okay, so maybe a reminder for those rectangular matrices, what is the row rank of A if n is not equals to m. Okay, so that will help you to understand how many non-trivial singular values can you have and so on, because basically those matrices will either have n by m dimension or m by m dimension, right? So that's the point of this exercise. And I started with discussing this normal condition. But basically what is important is that that even if you don't have a normal matrix, you can construct this matrix here. And the way to think about this, that's one last comment about the A dagger A, is that in complex numbers, we can construct Z star Z, and then for any Z in complex numbers, this is non-negative. So that's how we take modulus. So this A dagger A construction is similar to A dagger A. And here we also have this kind of notation. And you can look up something called Louvner order or PSD cone. That will be also somewhere on Wikipedia. Okay. That's just some simple things that for each one, if you look at the definitions, really the Wikipedia article will tell you everything. Okay, we will not need it today so much, but I wanted to say that if I have an operator A dagger A, which I cannot diagonalize, then A dagger A I can diagonalize. If I cannot diagonalize A, I can diagonalize A dagger A. And then if lambda is eigenvalue of A dagger A, then okay, maybe that's Python notation. Square root of lambda is a singular value of A. Okay, and if you check on Wikipedia singular values and so on, maybe one thing you want to check is that you find those kind of statements. And basically this is nice because if this diagonalization exists, so if this exists, then the norm A operator is max lambda. And then I will use spectrum notation. So lambda is in the spectrum of A, okay? But if I cannot diagonalize it, then I do this kind of normal operator construction. I will do A dagger A. I will diagonalize A dagger A. I will search for the largest eigenvalue of A dagger A. And then my operator norm will be the largest singular value. So the largest eigenvalue of A dagger A, if I take the square root, I will take my operator norm, okay? So just undoing the arrows now. And basically that's the most general discussion of this operator norm here, okay? So this is sometimes important, and now I can explain to you why the operator norm is unitarily invariant. Okay, for this we can have a couple of proofs. But I need this general definition to show also a more general property, namely UV dagger operator norm. Okay, so the difference here is that V might not be equal to U, and here we have just a regular unitarity transformation. Okay, so the first proof is that we can optimize over all wave functions psi, and then psi u dagger a u dagger here psi divided by psi. Okay, and if I maximize like this, I could also maximize over u psi, and then I could maximize over some different phi. And if I do this, I will just maximize like this, psi, or it's unitarily invariant. That's the point of using unitaries. So this is just forgetting that there was some relabeling of the maximization, and we get this. Okay, which is the operator norm of A. That's some invariance like this. This is very important for discussing Trotter-Suzuki bounds. Okay, that's actually relevant. And for the bounds that we will be discussing today, we will actually need this property as well. But let me give you another proof. So if I consider the operator norm squared, then this is the max lambda in spectrum of what? I'm squaring the maximum I. So this will be the, if I order eigenvalues of this operator. So singular values of this operator, if I order them, then this is the maximum maximum in the spectrum AV dagger, and then this I need to take Hermitian conjugate, and then again the same operator V dagger, and then maximum lambda, because I'm squaring and I need a square here. Okay, so I can directly go for this one. So, but this lambda is also the operator norm of U A V dagger U A V operator norm. But now it's because of this transition here. So no square. Okay, because I'm squaring the operator. If I'm squaring the operator, I don't square the norm here, and here I need to square it, right? Because I'm squaring here. Okay, but now you see that something will cancel. So I will have V dagger, A dagger, U dagger, U A V, and here a double dagger, right? I should have here a dagger and here a dagger. Operator. So we get what we were just proving just before now, A dagger A, V dagger operator norm. So this is the operator norm by unitary invariance. And this is lambda of A dagger A, the maximum eigenvalue. But we can also show that this is the maximum eigenvalue of A, or actually this is the singular value of A. Yeah. So basically we get that the maximum singular value of this one squared of this one is this one. So what we get is that the, let me just maybe put, so this, I'm computing too much and then there's a bit of a mess. So what we get is that this norm, where it is, okay. This norm is equal to this, but this is operator norm of A squared, okay? So I have this like sideways invariance, okay? So let me give you some examples. A operator is unitary A V operator, okay? So one example is U is identity and V is a unitary matrix. Okay, so I have a operator is equals to A times V, for example. Okay, so I can just multiply if on the edge of the operator, I can always put in a unitary operator. Okay, another example. Another example, U is equals to identity, and okay, maybe I do it differently. So example, we want to show that U operator norm is equals to 1. Okay, for all U in the set of unitary matrices. So this is the set of M in C D by D such that M dagger is the identity. Okay, that's the notation here. So how do we show this? Well, we use the previous example. So yeah, I have U operator is equals to U and any unitary V. That's our operator norm. So if I set V is equals to U dagger, then I have U dagger U is the operator norm of identity. And the maximum eigenvalue of this operator I know because it's already diagonal and has only one eigenvalue. Okay. So one trick. Okay. So maybe we try a different proof. So do we want a different proof? Yeah, maybe it's fine. Okay. Okay. So one confirmation question we had is whether for any unitary matrix we have operator norm equals to 1, and that's what we just proved because we only use the unitary invariance of the norm and we just added in this operator. Another proof that you can consider is to use, for example, A times B operator norm. It's another property if you have it. Yeah. So basically unitary operators behave in a weird way for the norms. So for example, we have this exact multiplicativity for the operator norm. So if we would take A is some unitary operator and B is maybe the U dagger, then we also would like to know that U dagger operator norm is equals to U. And that's quite simple because we said operator norms are ultimately singular values of some operator, right? And singular values are invariant unitarily, and singular values are invariant under just flipping the matrix, for example, right? So here this should be fine, yeah, but it could be also homework number. I just gave you a couple of proofs for this, so let's say this could be some homework number 2 to explore different options why all this stuff is consistent, and for example why this holds. Okay. So then from choosing this, we would have identity of the in the operator norm would be U operator norm squared, right? So for example, you can try to get it that way as well. Yeah. So previously I used unitary invariance. Here I'm using a stronger property that holds for any two matrices. This is multiplicativity, it's called. Multiplicative means that if I multiply we have this multiplicative property, which means if I multiply two operators, the operator norm of the multiplication is the multiplication of the norms. Okay, you can split like this. It's important to know those properties because, for example, in different quantum info proofs, you will be using this kind of stuff on and off. So it's good to know at least that you might be searching for some properties like this. And to prepare yourself for some work that you might be doing, it's good to know your Wikipedia. Yeah. So it would be good if you, for example, do homework 3 to find like a small proof of this or something like this. Let me give you one last example of how to show that unitary operator U has to have norm 1, because this will be the square root of max lambda of what? U dagger U. Okay, so this is max max lambda of the identity, right? And that's 1. Okay, so we can go also from this definition using the singular value. All right. And maybe as the last comment, I wrote down some definitions for the singular value decomposition. And you know, we should head on to maybe some exponentials, but it's worth your time. So for any operator A, I can find those unitary operators U and V, such that I will have a diagonal matrix here. Okay, and you see that if I consider A dagger A, then I will have what we were computing. So I will have V, and then I will have lambda squared and then V dagger. Okay, if this is too fast now, then it's optionally like homework 3, yeah, to compute with those kind of stuff. So you can look up, for example, what are the algorithms for singular value decomposition. Singular value decomposition is important for entanglement theory. It's important for different numerical procedures. Okay, so NumPy can run this numerically for you, but it's good to know how that works. And in some way, it is equivalent to diagonalization. That's something that I wanted to mention here for singular value decomposition. Okay, so maybe I will remember some more tricks for this, but now let's start considering unitary operators. Okay, so we were considering exponentials of A in the overview last time, and we gave 2 definitions. If A is a diagonalizable matrix, then it's exponential of lambda, which means that this is just rotating a matrix where I take e to lambda 1, e to lambda 2, and then e to lambda d, and then I have 0, that I just take this diagonal matrix and then rotate it back. Okay, so actually this is one idea how to compute numerically dynamics of some small spin chain. Yeah, so that's something that we do in quantum mechanics, but you can actually use this to compute, for example, what happens if I couple 2 qubits or 3 qubits with each other. So let's say I have some model and I have some Pauli matrices. I have Hamiltonian x1, x2 plus x2, x3. Plus z1 plus x2 plus y3. Okay, so if I would like to compute this numerically in NumPy, I would have to write down all those operators, and today I don't want to explain this too much, but you could use this diagonalization to compute e to IH t applied to psi. You could use this kind of diagonalization decomposition. So maybe we will not do this in terms of the eigenstates and so on, but one thing that we were kind of touching upon last time is to say that we have, for example, a series representation of the unitary operator. So we have just a to power n divided by n factorial. So we want to look at this a little bit today. But before we go maybe to some numerics questions later on, maybe next week or something, let's ask a question. If I change my my Hamiltonian here, for example, I will have Z1, Z3 times cosine omega t. So what happens? Well, we will have to do this Trotter-Suzuki decomposition that I will say in a moment. But for example, I could consider a Hamiltonian, a situation where I suddenly change the Hamiltonian, I evolve for time t with this Hamiltonian, and then I get a new Hamiltonian H prime, which is, for example, H plus 5 times this Z1, Z3, for example. Then the evolution chain would be psi e to IHT psi, and then e to IH prime t psi, and whatever I had before, right? HT on psi, okay? So now you could ask, can I write this as IH prime prime double prime t or something like this, psi, okay? So for example, what is H prime prime, okay? So let me pause the recording because this is a good question. So let me spend a minute to ask you if you know how to compute H prime. Okay, so we have a couple of ideas how to compute H prime prime, H double prime. The first idea from Norman is using BCH, and that's actually quite a nice homework to maybe have some trouble how to use it and like how it's difficult and so on. So maybe homework Wikipedia and try to cook up some strategy. If next time I ask you again, like, how would you do this? Like, what's going on? Another idea is that you can think about Lie group theory. So I want to tell you about this in a second. Another idea that you could do is, for example, can I use NumPy? Okay. And that's a great homework for you to consider this Hamiltonian that I gave you. Maybe we will do some examples. I will send you maybe some online. We can do some online notebook or something and you can try. So that could be homework 5. And let me tell you what kind of operations we would like to have. So let's say I have H double prime T should be equal to H T e to IH prime T, okay? So I have two evolutions composed together and I want to say, what is the joint Hamiltonian which at time T gives me exactly that, yeah? So what I could do is NumPy U1 and then NumPy U2 using linalg np.linalg.exp matrix or something like this. Yeah, so X matrix of HT and H prime T as well. You set it to U2 to be this, okay? Then when you have those together, you do np dot of U1 and U2, okay? And then you can try, for example, whether you will get some trouble with a matrix log. So log matrix, I don't remember the name because I never used it that way, I think. But it might be just log. So part of your homework would be to know whether you can quickly find it in the documentation and so on. If yes, then great. It means that you're prepared and great stuff. So U1 times U2. And then divide this by I times T. And that's something that I could call H double prime, right? Okay. So that's now maybe 3 ideas. There might be some more ideas on the way later. But I suspect that you will have trouble using the BCH formula in Wikipedia because it's not a formula, it's like a series. So it's kind of weird. And kind of you see that that the nonlinearity that you will find for BCH on Wikipedia is showing up here because you have to multiply two operators together and then take the logarithm of that matrix, which is a very nonlinear function. Yeah. Okay, so this should be fine. Maybe let's discuss how to take the logarithm of a unitary matrix. So how would I do this? Well, a unitary matrix is a normal operator. So I can diagonalize this matrix, I guess. It's maybe not so difficult to see. So if I would consider, we were looking at operator norm of unitary is 1, which means that the spectrum of any unitary operator is on the unit circle. So if I take a lambda here, it will be of the form I to phi, which is kind of the definition of a unitary operator, that its eigenvalues are all phases. Okay, so the eigenvalues of a unitary operator are not identity, because then it would be all identities. But for example, we can that way see that the identity is a unitary operator because all lambdas are equals to 1, so phi is equals to 0 in this notation. Yeah. Okay, so simple stuff here. So maybe what we need to do is to take log of e to phi 1 and then form a matrix log e to I phi d. Okay, and I hope that you are screaming because there's this trouble that basically I would have maybe I phi 1, I phi d, but for each one I can add 2 pi, right? Because, you know, I can add 2 pi to the phi and I will not change the whole thing. So here a reminder, complex analysis and logarithm of z in complex numbers. And there's something like, you know, those Riemann sheets and so on. So basically multi-valued functions. Is one question, okay? Which basically tells us that that taking this logarithm here in NumPy might be some problems for you, but I'm already telling you how to understand what might be going on. And if NumPy square root is running on some number like, I don't know, x, then actually this is giving us the plus square root of x, right? So if I consider the square root function of x, it could be plus minus x, right? Because I square this and I get x. Okay, that's one example of this multi-valued question. And logarithms, as a reminder, in complex analysis have this property as well. Okay. So this is a little bit to give you something to think about, and the answer will be that you will just have to be comfortable with your software. If you have any linear algebra software that takes matrix logarithms, you need to be aware that it might be selecting this primary Riemann sheet. So there's something called Riemann sheets in complex analysis, some kind of continuation of logarithms. You can look at nice pictures of complex logarithms and so on. Worth your time to remind yourself. Okay, so okay, I told you maybe some troubles ahead. How much time do we have? Okay, now I want to tell you one more thing about the okay, why h prime prime always exists. And the answer is Lie group theory. Okay, and I promised to be doing Trotter-Suzuki today, but I think we will come back to it in some time, and it can be a nice homework. So I think homework maybe number 5, to look it up on Wikipedia and try to get as far as you can. Why I'm talking about this is because I should explain to you all the details about the unitary group, but let's see if we can get ahead just by taking statements. So I wrote down this notation. The unitary group of dimension D is matrices which are complex valued, which are D by D, with the property that maybe I will write it like this: the inverse of this matrix always exists, and it's just a Hermitian conjugate. And we got some properties. So for example, for any group element, so small u in capital UD, which is a matrix, we have that the operator norm of u is equals to 1. They have a lot of properties, okay? And now the question, why is this group? The most important thing for a group is that if I have 2 group elements, G and G prime, so in our case, we are working with a representation of this unitary group. So those are just matrices. If I have 2 of them, then their multiplication G prime is again in the unitary group. Okay. And this will be important for Trotter-Suzuki. I mean, those kind of things are relevant, okay? So that I will just show it. Okay. So how do we show it? If we have this, then we know that there's the property G dagger is equals to G prime dagger is equals to the identity. So now let me try to see if G prime dagger times G prime together is the identity. Okay. If yes, then the property holds. Okay. Because unitary matrices are matrices so that taking the dagger gives you the inverse. So if we get this property, then we have so this inversion property already places them in the unitary group. Okay, that's some way of saying this. So I will have G prime, and I need to take the dagger. I have G with a dagger. I have G and G prime. I ditched the bracket, and the property is called associativity. Associativity of matrix multiplication. Okay. When I removed the bracket, I took a step, and I'm writing it out so that you see maybe in a more complicated setting that I'm actually doing mathematical steps in between, and maybe I'm doing them fast, but take note of this. If you will look at, for example, groups, there will be an associativity axiom as well somewhere. Okay. So I have this. So let me use this property that this is a unitary matrix. Okay. So I will get that this is G prime dagger, and I will be like very explicit. And then G prime dagger times G prime, because you just multiply the identity with this, right? And then the identity is here. Okay. So I got that if I take 2 elements of the unitary group, then if I do the group multiplication, which in this case is matrix multiplication because we are working with this representation, then this new matrix G double prime, which is formed from the multiplication, is again a unitary matrix, okay? And I can maybe scribble somewhere here. And this means that all G in the unitary group are of a form G is equals to ITH, okay? So basically taking exponentials of all Hermitian matrices gives me all unitary matrices, okay? And it goes vice versa. So I can get any unitary matrix by finding a good Hamiltonian, and then I have this, okay? So what we were doing in NumPy is actually implementing numerically a procedure which is known which is developed in Lie group theory, like how to find this generator. This generator in our case is just a Hamiltonian here, okay? So we kind of did a practical implementation very quickly, okay? But why this H prime exists is because the unitary group is a Lie group, and because it's a group, those GG primes are in the group, and Lie group means that you can form it essentially by exponentiating some Lie algebra, okay? So maybe let me squeeze in one final comment. So notice which one is the group property and which one is the Lie group property. And you know, you have Lie groups is, so to speak, exponentiating of Lie algebra. Okay. And if I will get feedback to talk more about Lie algebras, I will talk more about Lie algebras next time. But for now, I want to go to Trotter-Suzuki and explain a little bit more there. But check it on Wikipedia again. Like whatever term I'm writing down, actually trying to write it nicely, then check it on Wikipedia. All this stuff is described there. And basically what you will find is that the Lie algebra of the unitary group is I times Hermitian matrices. Hermitian matrices are Hamiltonian. So that's how you get from quantum mechanics to maybe geometry, Lie group theory, and so on. Okay. So now we have the statement that the Lie group is exponentials of Lie algebra. So if I know that G prime, oops, if I know that G prime is in the Lie group, okay, we were proving this here. If G prime is in the Lie group, then it has to be of the form that it's an exponential of some Hamiltonian, and we can call it H double prime. Okay, it's just using general theory in mathematics to know that this stuff exists. Okay, so if I have two Hermitian operators and I take the sum here, BET, then I would like to approximate this as EIT and EIBT. So will it be a good approximation? And then again, BCH, only if AB is equals to 0. Okay. So what happens if they are non-commutative? And if they are non-commutative, then we consider a limit case. And now I could explain to you taking the bounds, but I think I want to. So I will take 15 minutes to explain to you the proof ideas and what is behind the proof that if I take the limit of n to infinity of e to IAT divided by n, e to IAT divided by n to power n, that I will get e to a plus b times t. Okay. So what does it mean to take the limit and so on? Basically, what I wrote down is the Lee-Trotter formula, Lee-Trotter-Suzuki, I think. So Lie groups exist with this name because there was a mathematician. So they take the name from the mathematician that studied what happens if you take those exponentials and so on. And then Lie algebras are kind of directions in which you can exponentiate so Lie groups are geometric in the sense that they are differentiable manifolds, and on a manifold I can consider the tangent space, and the Lie algebra tells you what is the scope, in which directions I can kind of rotate, what are my possible arrows. And for example, this Lie algebra can have a basis. For us, the basis for the Lie algebra are, for example, the Pauli matrices. So that's why our Hamiltonian in the example, I was just quickly writing it here. You will find Hamiltonians like this. And the meaning of this is that Pauli operators are a basis for the Lie algebra. Okay. So I will not say much more because we want to talk about this a bit more. So you have Lie, Trotter, Suzuki decomposition. Suzuki also published some papers more recently. Lie group theory is more than 100 years old, and that's the kind of stuff you can look up on Wikipedia and kind of look at the history of this. So we have this stuff. Now, one question is, what does this limit mean? What is this limit? Okay, and this limit means that if I form a unitary operator with label n, which will be EA, Tn, E to I, sorry, this is, this should be B. Otherwise it will be quite trivial. Btn divided by n, and then to power n. Then if the limit of real numbers which are obtained using the operator norm, e to ia plus bt, if that goes to 0. So if this, then a limit of un is equal to our u. Okay, so our u is explicitly a plus b. Okay, that's the definition of taking that limit. But you see, we can do it in a smarter way. So we will have, in general, we will have a violation of this equality, but you could already start asking questions. Okay, so let's say I have EIA T and then EIB T, and this is not equal to EIA plus B T, then what it is equal to, right? So you could write E to I, A, and maybe some star product T. And A star product would be just like a D by D matrix, which is Hermitian. Like this, okay? So basically I could define a star operation, which is, okay, if I would write F, okay. If I would write H prime to be basically such that E to IAT, E to IBT, right? Then it would be clear. Now, what does this H prime matrix depend on? HB. So if I write A prime AB, then basically I have a function of two matrices and I get a new Hermitian matrix, right? So I could also define a star operation, which takes a D by D Hermitian matrix and then another D by D Hermitian matrix, and gives me a D by D Hermitian matrix. So I could define the set of Hermitian matrices as Hermitian on CD by D. And I could also define this as like, I don't know, H dagger D. And this set is all matrices M, which are complex D by D, such that M is equals to M dagger. Okay. Those kind of sets writing, I'm writing explicitly because it's useful. If you will look at Wikipedia, it's a useful thing to do. So alternatively, I could write this star product as a mapping of this Hermitian matrices and getting a new Hermitian matrix. Yeah. And my point here is to remind you of this notation. So basically, if I have two matrices coming in, one matrix, second matrix, and I have a new matrix coming in, then I could say that this association from two matrices building a new matrix is a mapping, yeah? And it takes two matrices and gives me a new matrix, so I can define the domain of that function and the image of that function, right? So going back to analysis, the same thing we can do for matrices, okay? It's a bit of an overkill, but like that's just to tell you the trivial definitions, just so that you can set up some more mathematics. And I wrote down this here so that you see that here, this is together, and that's this is together, and that's this. So let me erase the unnecessary stuff. Okay, so basically what we get is a special product, and on Wikipedia you might be actually able to find it somewhere in the Lie group theory that sometimes you define this kind of twisting product that gives you this new element of the Lie algebra, right? Because the idea is that if I want to compose two elements of my unitary group together, I should be able to get a new element of the Lie algebra such that this holds here. Okay, so that's maybe okay. Anyway, so I wanted to be explaining this stuff. So this is maybe more general looking at that. Now what I want to show is, first of all, okay, maybe I will be writing in blue. If I will write u is equals to limit n going to infinity of e a, and I forget t for now, e a b divided by n to power n, then this is a d by d matrix. And now question, is u dagger inverse of, so maybe written this way, is the inverse unitary for this limit, right? And that's not so obvious because I took infinitely many matrices, I multiplied infinitely many matrices with each other, so how can I know? Okay. And that's again something you can go back to analysis on Wikipedia because it will be the same thing. And just to explain you that those limits are actually not you know, something that you can work with. Okay, so I will give you this example to say, how do I multiply u dagger? So spelling it out, I have limit n going to infinity e to ia divided by n e to ib divided by n, the whole thing to infinity. That's one thing. And then another thing is that I have this matrix here, e to ia divided by n, e to ie divided by n. And I have the Hermitian conjugate. That's what it means when you write it down, okay? So now one question, can I consider can I consider e to ia n, e to ib n dagger maybe at the end? This. Let me write it more nicely, but the brackets are getting impossibly large. Okay, some challenge here. Okay, so what I'm changing as the ordering, this is not necessarily the same. Okay, it is actually the same. But maybe let's forget about this. I just want to indicate to you how to work with the stuff. So in standard analysis, you will have something like this. A limit an times bn is the limit of an times limit of bn. Okay, so I cannot see you on video, but I'm assuming that and here maybe I will write m to make it explicit, bm. Okay, so this is how we are actually working with limits, right? There are certain properties of taking limits in analysis, so that if you have two limit cases, which is a, b, then the multiplication of the limits you can obtain as taking the limit of multiplying the sequence elements. Okay, so let's prove this. So let's just write this, that this is u dagger, and maybe I can squeeze it on the same page somewhere here. So if I would consider now the limit of n going to infinity, e to ia divided by n, e to ib divided by n to power n times e to minus b divided by n, e to minus a divided by n to power n. Okay, so here and here I need to do to power n, and here the dagger operation, the conjugate, the Hermitian conjugate. Okay, and in this operation we see that this is limit of n going to infinity of the identity, which is the identity. Okay, constant matrix. But you see what the operation that I did here is a matrix value generalization of like complex sequences, complex or real sequences, right? So in regular analysis we study it for one dimension, but then it's called actually topology of a normed vector space. So basically the norm gives a vector space some topology. When you have topology, you can consider sequences, and that's what we are doing with this operator norm. Okay, let's look here. Here, this is telling us what it means that a sequence of matrices converges. It means that the sequence of the norms of the differences converges to 0. Okay, so as I'm increasing n in my sequence of matrices, the difference in operator norm from my target matrix is going to 0. So this un converges. We could write un goes to u. Okay, but we do this by mapping the problem to the convergence towards 0 of a real sequence. Okay, so I could call this as limit of some sequence delta n is 0, and delta n is basically this norm. Okay, so this is how we work with sequences of matrices. Basically we consider a matrix norm, and if the norm of the deviations goes to 0, we define this limit here. Okay, This is what it means to have the limit of matrices. Okay. And now once we have limits of different objects, as in analysis, we have those properties, and those properties you have to prove. But because of that construction, everything is inherited. Okay, so it becomes quite nice. So now we proved, for example, that if I consider the Trotter-Suzuki decomposition, it will remain unitary. Okay, so yeah. Okay, let me finish by telling you a beautiful bound, and that will prepare considering a bound on the convergence. So this is just what we said here, tells us that we converge to something. Okay, so basically this is the statement. This is convergence, but not convergence rate. Okay, we don't know how fast, how large does it end, you know, if I want them to be epsilon close together, how big do I need to have this n? If n is infinite, it's like any, it's zero difference. But if it's not infinite, then it's not, then we don't know yet. But let me show you one example. So I need to take e to power ia, and then I want to take e to b. Like this. And then I want to show that this is smaller or equal a minus, where a is equals to a dagger, b is equals to b dagger, which means that e to ia and e to ib are unitary operators. Okay, so homework 6, you know, ia ud, then maybe you can consider y. It's actually an interesting proof. For example, you could use the series definition or something. You can try to use those different properties to prove this. Okay, so it can get more complicated, but let's consider a proof whether I can get it right. So let me consider a construction like this: ITA, and then times e to I one. No, I need t minus 1, I think. T minus, no, 1 minus t, I need 1 minus tb. Okay, b, this I erase, and I define qt. Okay, so this qt is a mapping of t ranging from 0 to 1, and then it maps into the unitary group because we multiply two unitary operators. And you could also write that qt, you know, basically t taken from 0 and 1 gives me, is mapped to eita, e to I1 minus tb. So what do I get? Q of 0 is, this is 0, then I have e to ib. Q of 1 is e to ia. Okay. And I was making this explicit because this is a very good notation to show that we have an interpolation going on. So let me tell you a little bit about interpolations. Let's say I have one vector here and one vector here, and I want to connect them on this line, okay? So let's say this is vector A and this is vector B. So what I could consider is what happens if I multiply TA and 1 minus TB. And you will see that T ranging from 0 to 1 is basically moving a particle on this interval here. Okay, so this T is a little bit of a zipper which continuously allows me to move between A and B. Okay, that would be interpolation. That would be linear interpolation. And again, if I write something in a word, then there's a good Wikipedia article. I know because I always use Wikipedia. I'm not exactly sure how the article looks, but this is something for Wikipedia, okay? So what I wrote down here is, first of all, a non-linear interpolation. Why? Because depending on those operators, if I move continuously this T from 0 to 1, sometimes I will be actually a little bit closer to A than I will be close to B, okay? And because of BCH, it's not just connecting them. So for example, if I have the trivial case where A, B commute together, right? Then it would be a very simple problem. And then I would have e to ita plus I1 minus tb, okay? And that would be an exponential of the linear, that's an exponential of linear interpolation. But because there's this exponential going on, we don't have a linear interpolation in our QT formula, okay? One thing to note, there's a difference between linear interpolation and the interpolation that we do, okay? So now we want to prove this very important lemma here, okay? And what it says is that if I have one Hamiltonian EIH and I have another Hamiltonian perturbed by V, then the unitary evolutions that I will get will be different at most by the operator norm of this perturbation that I have here. So it's a perturbation, it's a general lemma allowing you to bound how strong a perturbation can change dynamics. Okay, that's what we will prove now. Okay, so what we were setting up is that I have actually Q0 minus Q1. I just go back and show you. I was computing it here. I have Q0, which is this, and I have Q1, which is this. So if I take the difference between those two, I have this, okay? And this I can write as the integral of 0 until t dt, and then the derivative of qt over time, okay? So now what's happening is we have the fundamental, I'm writing, so that's your Wikipedia, fundamental theorem of analysis. If a function g is equals to f prime, then the I have, sorry, I'm already getting tired, 0 to 1. Then the integral from ab dx g of x is equals to fb minus fa. Okay, so now I did the same thing for matrices. How do you define a derivative? Define dt of qt. Okay, I can do this by taking the limit of epsilon going to 0, qt plus epsilon minus qt divided by epsilon. For example, right? What does it mean to take this limit? It means that I can find a matrix. I can find a matrix that I will designate as this, such that if I take this norm minus the finite quotient plus epsilon, t divided by epsilon, I take the operator norm of this, then this goes, this is a sequence of real numbers, right? It's and basically that goes to 0, right? So again, the same definitions, yeah? That's why I can do the fundamental theorem of analysis, or actually this is of calculus. I can also do calculus for matrix history, okay? Okay. So I have this, and now I told you about associativity. I told you about a unitary invariance. I told you about multiplicativity. I told you definitions of the operator norms. I didn't tell you about the triangle inequality. And triangle inequality is just an inequality, so there shouldn't be an equal sign. Inequality A plus B. Okay, so now I have that EIA minus EIB is equals, this is with equality, integral 0 to 1 dt, derivative of dt qt. Okay, and this continuous integration you can write as a Riemann sum because we have continuous functions. So actually you will see that you have from 0 to 1, and now with an inequality, because it's just a generalization of the triangle inequality to an integral, okay? And then we can consider dt qt. Okay? And now we are almost done, because now I can also use calculus to compute derivatives of matrices, okay? So you never compute by definition, you don't compute derivatives of functions. Also for those matrix exponentials, we don't compute them. So first I will use the Leibniz rule. So dt of both sides. So I want to consider dt of ita, bracket here, and I need to do a lot of writing, 1 minus tb. And Leibniz rules tells me plus, repeat whatever I did there, but without the derivative, and apply the derivative to the other factor. Okay, right? And again, note that this is the same as the Leibniz rule for dtfg is dt, I don't know, f prime g plus g prime f, but the non-commutative case. Okay, so I have it e to it a, and then I have an a here, and I don't have the t here, sorry. To erase this. So I have I times a e to ita, and then this one stayed as it was, 1 minus tb, and then I have plus e to ita, okay, and then I will have and okay, I will have this here. I will be explaining maybe more than we need, but okay. 1 minus t, so the derivative of 1 minus t is minus t, minus 1 here, times b. This is important because this will give us the ultimate minus sign. Okay, so this is commuting with that one. I can pull out outside, and then I have IT A e to I 1 minus T B plus e to I minus, maybe I will put there, the minus I have here. I'm kind of writing this very explicitly, minus T. Okay. So now I can do some whiteboard tricks, finally something fast. So I can erase this, and I can erase this. And now you will see why we have this. Ta-da. Okay. So to recap, I have the perturbation formula for saying I have two different evolutions with generators A and B. This is with equality the integral, but if I use the triangle inequality, I have to integrate what it means from 0 and 1, the norm of this. So we started computing this stuff here. Okay, we computed here. And the derivative here is I times this unitary operator, then difference A minus B and this. Okay, so let me repeat this. And we are almost done. So I'm just slowing down now so that maybe everything is there. So we have this inequality integrating dt 0 to 1 norm dt qt. Okay. And so we have the bound. We have the bound here. I still need to integrate 0 to 1 dt, and now you will see that everything is falling into place. So e to I t a, then a minus b e to I 1 minus t b. Operator norm. Operator norm. Ta-da. Okay, so now maybe we pause and see if you see which property we need to use. Okay, so we will use the property that U is defined to ITA, V is going to be defined I1 minus TB, and I guess we had some B dagger, and we had this property EA. Now it will be EA minus B. V dagger operator norm is with equality here A minus B. That's norm invariance of the operator norm. So what are we integrating? We are integrating something beautiful that doesn't depend on T. And I will just simply have, there's nothing to write, A minus B operator norm, which is A minus B. Ta-da. Okay, a long session today, but we got here. Very important formula. Proving the convergence of Trotter-Suzuki is making it more complicated. Okay, but this is showing you the full power of this nonlinear interpolation. We touched on the linear interpolation and so on. Okay, so we arrived at this inequality because there was one inequality in the chain. This is smaller or equal than this. Okay, this is smaller or equal than this, which is exactly what we wanted. Is kind of this formula, or it's this formula. Okay. Good. Then we are almost done, I guess. So that's our beautiful bound here. I will give you now one more homework. Homework 500. Prove I times A is equals to A using unitary invariance. Let's see if you can find a proof. I think it's possible to prove it. Yeah. That's a tricky bit, but we'll give you some ideas how to work with the exponentials. And here it will be quite a trivial exercise. But I'm liking this exercise. So this is just to say that there was this I. Normally we would drop it by one of the axioms of the norm. But this unitary invariance is kind of the key feature today. That's what we were using today in the key step of the proof. I mean, this here is absolutely complicated and terrible. If it wasn't for the norm invariance under unitary transformations, we wouldn't get an integral of a constant. Yeah. So in the last equality where we arrive at the last relation here, this is just the integral of a constant, and integral from 0 to 1, so it's 1 times the constant. Yeah. So norm invariance is really key, and that's why we are considering this beautiful idea here with non-linear interpolation. Okay, I'm not doing a recap because it was a long session. Okay, so then maybe we finish here. Okay.